All right, guys, let's use some of this integration stuff to do some things, right? That's what this whole chapter is really about, is applications of integration. And so as you saw in 6.2, because you've read the lecture, I know some of the math in it is a little hard to maybe follow. But the whole idea here is that this is the whole idea of integration, right? Is taking, we talked about area under curves, and taking a lot of rectangles, an infinite number of them, to estimate area. So that's what we're doing now. We're just going to do that between two functions. So if you look at the discussion in the book, really how do we find the height of a rectangle that represents the area in between two functions? We just take the difference between those two functions, and that gives us the height of a representative rectangle. So I'm going to do 3 examples, I think, for you. 2 with respect to x, 1 with respect to y, and then we'll call it good. So let's go ahead and start off with the first example. So let's find the area of the region. So we'll start off kind of easy, and of course you looked at all your examples in the book, which is great, of the region bounded by or enclosed by the functions. We'll start off kind of easy. Y equals x squared and y equals 2x minus x squared. All right, so the first thing we need to do, because we weren't given specific x values for where to find this, is it says it's the region enclosed by these two functions, so they must meet somewhere, right? Or else we're going to have an infinite area, and that's not going to be very helpful. They might tell you to find the area between two functions, but then they're going to have to give you x values, or all have to give you x values if those functions don't intersect. So what I want to do first is I want to see where these two functions intersect. And so basically what I'm asking is, for what x values do I get the same y value, right? That's what that's asking. And so I'm going to set my y values equal to each other, basically set my function equal to each other. So if I add the x squared over and subtract the 2x, right, I understand that sometimes this is the hardest part of calculus, is the algebra. So sometimes I like to show you some of these and not just assume that you know that algebra right off the top of your head, because maybe you're not like me, maybe you don't do algebra for fun, which I'm sorry for your sad life. I'm just kidding. Just kidding. All right, so it looks like these two functions are going to meet at 0 and 1. I know that this is a parabola facing up. I know that this is a parabola facing down with it maybe shifted around a little bit because of that 2x. So let's go ahead and graph this, and because I know I'm going between 0 and 1, and that's a relatively small area, I'm going to kind of zoom in on that 0 to 1. So let me go ahead and make an x and y axis, and we'll graph this thing. Okay, all right, so there's my xy axis. Not perfect. What in life is, right? And so let's graph these. So I'm going to go ahead and graph x squared. I know x squared goes through 0, 0, obviously. And notice I kind of zoomed in on the 0, 1, because I know that's where they're going to meet, right? So you're going to need to know how to graph some of these. You can use a graphing calculator. You're not going to be able to use like Desmos or anything. Obviously, I can't control you being on the internet, and so I can't quite do that. So at 1/2, I'm at a 4th. And so this is a typical, oh man, you guys are this is going to be a bit of a lesson in imagination here in this class. Wait till I start drawing 3 dimensions in the next section. Oh, you guys, that was really bad. Let's try that again. I'll also graph this for you on Desmos, but it doesn't have to be perfect. Yours don't have to be perfect either. So there's my y equals x squared. Again, I know y equals x squared goes like this, so I could do a quick little sketch of it over here too. That would be fine. Obviously, that's not a great picture of it, but I don't really care that much because I know that they're going to meet at 0 and 1. And then let's look at 2x minus x squared. So if I put in some values for 2x minus x squared, if I put in 0, it also goes through 0. If I put in 1, obviously it's going to go through 1 also, right? Those, we know that's where they meet. Let's put in maybe 2, right? So if I put in 2, I see that I get 4 minus 4, which is 0. So it comes back down right here. So it looks like, I know this is a parabola facing down. So it looks like this parabola, must do something like this. And it does. You could verify that. So not a perfect picture, but it works, right? I just need a picture to kind of see what's happening. And the big reason I need this picture is because remember when we take this area, I need to know which function is larger than the other function. So I want to find this area right here. And what I like to do is I like to draw lines that represent, you know, like a box. So if I were to take a representative rectangle like we saw in your book, I want to know how would I find the area of this rectangle right here. Well, it looks like I would take the blue minus the pink, and sure enough, that's what we're going to do. Okay, so draw those lines the way that they should go, and let's see if we can find this area. And so by the way my lines are and the way my box looks like, this indicates to me that I'm going to be adding up those little rectangles, right? Where am I adding up these rectangles from? Well, I can take these rectangles from 0 to 1. That's where I can grab these rectangles. And I'm going in the x direction, right? Because I'm stacking these vertically along the x-axis. The function that's going to go first is the 2x minus x squared, because that's the blue graph, and then minus whatever that pink graph is, which is x squared dx. So once you actually get to this point, that's where it becomes pretty easy, where you're just doing a pretty simple antiderivative. These antiderivatives aren't going to be super complicated. Some of them might be a little bit more than the others, but then I get 2x minus 2x squared, right, dx. Take that antiderivative. We get x squared minus 2/3 x cubed evaluated from 0 to 1. All right, if I put in 1, I get 1 minus 2/3. If I put in 0, it looks to me like I get 0, so 1 minus 2/3 is 1/3, and I think we have the right area there. So I hope that makes sense. I hope you can see where that kind of comes from and how we can draw that picture. Now in Desmos, I just love Desmos. You can get an app on your phone for Desmos also. But we can see that in Desmos, we can verify y equals x squared, right? And then y equals 2x minus x squared. Oh, I should put a squared in there. And we can see that, sure enough, it looks like our graph was what we thought it should be, right? Much, much nicer than the graph that I drew you. But you're going to have to graph these by hand. So, you know, that's part of it. So I hope that makes sense. And you can see, again, we're going to be stacking these rectangles, right, along the x-axis. So we're integrating with respect to x. Let's look at one more example with respect to x, and then I want to look at an example with respect to y, because those can be pretty tricky. So let's do another example of finding the area bounded by a region. Find the area of the region bounded by the functions all right, what two functions are we going to do? Let's do sine and cosine. So bounded by the functions y equals sine of x, y equals cosine of x. Now, if I just told you this, you would just tell me right away infinity, because I don't have any bounds. So I'm going to give you a couple more functions. I'm going to tell you x equals 0 and x equals pi over 2. Okay, so this really is just a way of saying, like, I just want to go between 0 and pi over 2, but that's how we get that function. So let's kind of graph these first, and then I'm going to figure out where they meet, because I'm not sure. Maybe they don't meet between 0 and pi over 2. They do. But maybe they don't, right? And I'm not quite sure what's going to happen here. So let's go ahead and graph these between 0 and pi over 2 and see what happens. So I'm going to make my x and y plane again. 1.5. So go out a little further. All right, so here's my little XY axis here. Not perfect, but close enough. Just, you know, a little hint. Pi over 2 is about 1.57, or yeah, pi over 2. So usually wherever I kind of put my 1 and my -1, I go a little bit more than that for the distance between 0 and pi over 2. So let's see what I have here. So I want the area of the region bounded by the functions y equals sine, cosine, x equals 0. So x equals 0 is just the y-axis, right? And x equals pi over 2 is just going to be a vertical line at pi over 2. So let's kind of look at sine and see what happens. So sine, I know, is going to go through 0. Sine of 0 is 0. And then I also know that sine of pi over 3 or pi over 6, right, about third is 1/2. So I know I'm going to be about right here. And then I know that pi over 4, right, so here's pi over 4. Wow, that was a little bit. Pi over 4 is root 2 over 2, which is, oh, I should know this, like 0.7, I think. I'm just going to verify that. Yeah, 0.7. So at pi over 4, I'm a little bit closer to 1, right? And then I know at pi over 2, I'm actually at 1, and then it continues in its periodic nature to go like this. And we're kind of zooming in on sine here, so that's why my curve is so kind of big. But there's my sine of x. Actually, I'm not too sad about that. That's pretty good. Now, cosine of x. So here's this is y equals sine of x. Now let's look at cosine of x. Cosine of x, I know, hits 1/2 at pi over 3. So it's going to be 1/2 right about here. I also know cosine of 0 is 1. And I know that the cosine of pi over 2 is 0. So it looks like cosine is going to do something. And what do I also know? I know that the cosine of pi over 4 is root 2 over 2, which is about 0.7. So here is my cosine of x. And there are my two functions. And so now the reason I wanted to do this one, of course, is because it's an interesting one, because the actual sign, whichever function is on top, changes. Now I have some symmetry here, but I'm not going to really consider the symmetry right now, because what I want to just think about is, what am I going to have to do to define this area? So what I like to think of this as is I like to think of this as, I have this area right here. I'm going to call that a sub 1, and I'm going to call this a sub 2. Okay. Why do I have to break these up? Because if you notice, if I take a representative rectangle, right here for a1, which function is greater than the other functions? So if I look at this area right here, I have cosine is greater than sine for a1. I could just kind of draw a bunch of rectangles with no width. And then for a2, though, if you notice, what happens is sine now becomes greater than cosine between pi over 4 and pi over 2. So if I look at a representative rectangle here, right, I see that sine is greater. So if I want to find these areas, I must take the area of sub 1 plus the area a sub 2 to find those areas. I can't just integrate from 0 to pi over 2 of like sine minus cosine or cosine minus sine, right? Because they switch. So you will get the incorrect answer if you do that. I know there's some symmetry here. I could utilize that, but just because we're kind of starting this off, I'm going to do this one by one. So I see they meet at pi over 4. How could you have seen that before? Well, I could set these two equal to each other. There's not a whole lot of work to do here. Really what you just want to look at is, well, where are sine and cosine equal in the first quadrant, right? Because 0 to pi over 2 is that first quadrant right there. And where are they equal? They're equal at pi over 4. So I'm going to integrate from 0 to pi over 4. First, I'm going to do cosine of x minus sine of x dx. Notice I have, well, I might have good notation. Notice my good notation here, right? I have a dx because I have this integral, and then I have plus. Now I'm going to go from pi over 4 to pi over 2 sine of x minus cosine of x, because those functions switch which one is larger than the other at pi over 4. All right, now we're getting good to go. Antiderivative of cosine is sine. Antiderivative of a negative sign is a positive cosine, because remember the derivative of cosine is a negative sign, evaluated from 0 to pi over 4, plus antiderivative of sine is a negative cosine. Antiderivative of negative cosine is a negative sine, and this guy's going to go from pi over 4 to pi over 2. Okay, I'm going to just throw some parentheses around those. Don't really have to, but... Okay, look at this. This is good notation. I am a little picky about notation. I think I've mentioned that a couple times. All right, so let's put in pi over 4. Sine of pi over 4 is root 2 over 2. Cosine of pi over 4 is root 2 over 2. Minus, right? Let's put in 0. Sine of 0 is 0. Cosine of 0 is 1. So don't just assume that because we're putting in 0, it's going to 0. Plus, let's put in pi over 2. Cosine of pi over 2 is 0. Negative, let's see, sine of pi over 2 is 1, so that's minus 1. Minus, and then of course if we put in pi over 4, we get root 2 over 2, root 2 over 2, right? So let's see what happens here. If I add these together, I get root 2, right? Because I have half of root 2 plus another half of root 2 is a whole root 2. Minus 1. This one's minus 1 also. And then this right here is a negative root 2, right? And that becomes a positive root 2. So it looks like we get 2 root 2's minus 2. That is our area, okay? And if we wanted to do an approximation of that, which this is definitely a time when that might make sense, it's approximately, especially because we're talking about area 8 to 8. I mean, I'd like you to go to Home Depot and tell them like, I have a point, or I have a 2 root 2 minus 2 square yard, whatever I need to do. You should do that and just see what happens. I don't make friends at Home Depot when I make jokes about that. Anyway, that's my area. That's my answer. This is my exact answer. That's my approximate answer. I will try and be clear on a test anyway. Sometimes on the fun sheets, I don't always say on whether I want an exact or a you know what I'm trying to say, an exact or approximate. Oh my goodness, I am so sorry. Okay, one more example, and we gotta do an example of integrating with respect to y, because it's just tricky. It's really hard to get your mind to think about integrating with respect to y, right? It's just kind of a tough one to do. So let's do an example. Okay, so last example here. Find the area of the region. Same thing. Bounded by or enclosed by. All right, so we got a couple functions here. So here are the functions we have. Let's look at y equals x minus 1. And this is going to look a little bit weird, but I'm going to write this as y squared equals 2x plus 6. Okay. So here's the thing with one like this. So let's go ahead and get our xy coordinate system ready to go. Okay, don't look at this too closely because don't look at this too closely because my tick marks aren't quite exact. I just kind of handed these. Okay, so I'm going to just graph y equals x minus 1. So I know I'm going to be down at 1, right? And I know I have slope 1, 1. So again, not perfect clearly because my tick marks aren't that great. Look at this cool ruler that this has. But I can at least use a ruler for it because drawing lines is something that I'm not very good at. So there's my line, y equals x minus 1. And now y squared equals 2x plus 1 can be a little bit tricky, okay? But let's see if we can kind of figure out what's going on here. So if I do a little bit of work down here, so I could plug in x values and find y, but that's going to be a little bit tricky to do. So I'm actually going to plug in y values and see what my x's are. So like, for example, if I let y equals 0, right, then I get 0 equals 2x plus 6. So when y is 0, it looks like x is going to be what? -3, right? So at -3, or when y is 0, I get x to be -3. If y is, let's say, 2. So if y is 2, so let's set y equal to 2, then I get 4 equals 2x plus 6. So if I subtract the 6 and divide by 2, it looks like x is -1. So when y is 2, x is -1. Well, that's going to be the same when y is -2 also, right? Because when I square -2, I'm also going to get a +4. So it looks like when I have y -2, I also get -1 here. And so you can kind of see what's going to happen here. This is going to be a parabola. That makes sense because I have a y squared, but it's not going to be a parabola in the sense that we're going to have a parabola like we have here. What our parabola is going to do is it's actually going to be something like this, okay? So when I graph these, you know, I could, if I wanted to graph this like in my calculator, you could solve for y. And if you notice, y is going to, I'm going to take the square root of both sides. So I get actually a positive root 2x plus 6, and I would get a negative root 2x plus 6. And what that gives us is it gives us something that's not a function in terms of x, right? So this gives us something where we have to kind of turn our head to the side, and we'll see we get something that makes a parabola on its side. Desmos does a great job. You can actually graph this in Desmos. It's amazing. So let's go ahead and look at Desmos really quick. I'm going to clear these out. And I'm going to actually show you this so you can see it. But I'm going to do y equals x minus 1, and then I'm going to do y squared equals 2x plus 6. So we're a little bit spoiled by Desmos because it does it for us automatically. Unfortunately, you'll go get Desmos on the exam. So you're going to need to know how to graph using in the y direction. Or y is your independent variable and x is your dependent variable. It's not too hard to do, just plug in some numbers, right? And you can figure that out. So if I look at the graph of this in Desmos, you can see it looks to me like they are going to meet when y is equal to 4, right? And when y is equal to -2. But let's just verify that and let's graph that really quick. So I'm going to graph this 5, 4 on my page so that we have kind of the same thing here. So at 5, 4, right? It looks like we have that. And then because my graph was so off here, these are supposed to meet here at -2. It's because my units are off. That's why. Oh, whoa. Sorry about this. That's why it's not really working out exactly, because I handed my units. But I'm going to get kind of a cool looking parabolic shape that goes a little something like this. Okay, and so there's the graph of my function, and I'm going to verify, right, that we do meet at y equals 4 and y equals -2. But let's think about this for a little bit, and let's talk about why we want to integrate with respect to y. If you notice, if I try and make my rectangles in the way that I'm used to doing this, right, like this, notice what's happening here. This rectangle here is bounded by root 2x plus 6 and a negative root 2x plus 6. And then if I look at a rectangle here, I'm bounded by root 2x plus 6 and then the line x minus 1. So what x minus 1? I would have to do two separate areas than if I were to evaluate the integral in my comfort zone, which is probably to stack up rectangles along the x-axis. That is too much work. So what I want to do is get rid of all those. And what I actually want to do is I want to stack my rectangles along the y-axis. See how, not along the y-axis necessarily, but vertically. See if I stack rectangles vertically, these are not perfect, but do you notice that each length of my rectangle on its side, right, is bounded on the right by the line and is bounded on the left by, whoa, I got a little too excited over here, by the parabola. That's a good thing, you guys. This is nice because what that allows us to do then is just have one integral where I take the pink line, right? Which if I solve this for x, I could think of this as x equals y plus 1. And then I could subtract the green function, which if I solve for x here, right, let's solve that for x. X would be what, 1/2, right, y squared minus 3. So if I subtract that 6 and divide everything by 2. So if I stack this in the y direction, notice how much easier the calculus is going to be. I'm only going to have one integral. I don't have to split this up into 2 integrals, and I'm not taking the antiderivative or the integral of a square root. What a pain, right? We don't want to take the integral of a square root. That's a pain. So let's do this. So looking in the y direction can be very, very, very useful in terms of your area. So what you want to think about, though, and we're going to see this in the next section also, is you got to think about, where can I take these rectangles, right? Where are these rectangles? And I'm stacking these in the vertical direction. So my rectangles, right, can start down here at y equals -2. That's where I can start my first rectangle, which will really be 0. And then where can I stack these? I'm stacking up until here, which is 4, right? Oh, well, let's make sure that that is true. It's -2 and 4. I meant to do that before. So let's verify that those are going to be my bounds. So I'm going to set my 2 functions equal to each other. Okay, so I'm going to set, because I know sometimes the algebra is the hard part. I'm going to set these 2 functions equal to each other. This is a quadratic, so I'm going to go ahead and move everything over to the left-hand side. So I get 1/2 y squared minus y. So if I subtract 1, I get -4 equals 0. I sure don't want to try and factor that, so I'm going to multiply everything by 2. On the right and left, that gives me y squared minus 2y minus 8, right, equals 0. That gives me y minus 4 times y plus 2. You guys, if what I just did to factor that mystifies you beyond belief, you have to email me and you have to contact me, and we need to talk about how to factor, because you have to be able to factor. You're in Calc 2. You got to be able to factor, guys. You have to do it. All right, so sure enough, right, they met at the -2 and the 4, and the algebra verifies that for me. So now I'm ready to go. I'm going to integrate from -2 to 4. And now let's figure out which function's going to be bigger than the other. Well, notice, right, we plug in y values and it spits out x values. So don't overthink this. Don't overthink this too much, okay? If you look at a representative rectangle, like right here and right here, oh, that's hard to see, but if I look at this representative rectangle, right, it's in the x direction. So what value, where are my x values bigger, to the right or to the left? Well, on a real number line, right, numbers to the right are bigger than numbers to the left. So I'm going to take the pink line. That's going to be my bigger number than the green line, right? Just like vertically, if you're higher, it's bigger than lower. So same thing here. I'm going to take the line, which was y plus 1, and I'm going to subtract the parabola, which is 1/2 y squared minus 3. Please, 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 please be mindful of parentheses. I'm going to say this a lot in this class. Parentheses are important. You're going to see it written on your homework quizzes. Parentheses are important. Because if I don't put those parentheses, right, then that negative I don't subtract the whole function. I'm going to simplify this a little bit before I take the antiderivative. I know some of you just go ahead and take the antiderivative right away. You're welcome to do that, but I don't trust myself to do that and not make a mistake. So I'm going to go ahead and take the negative through, combine some like terms, and now we're cooking with gas. Let's take the antiderivative. So I get a negative, what, 1/6 y cubed, right? Because I would divide by that 3, plus 1/2 y squared, plus 4y, all evaluated from -2 to 4. Good. And then we'll put in the 4. That's what, 64 plus 4 squared is 16 divided by 2 is 8. Plus 16 minus parentheses, right? -2 squared is a positive, or -8, and that negative cancels. So I get 8/6. I'll deal with all this in a moment. -2 squared is 4 divided by 2 is 2, and then minus 8. And once we simplify all of this, we get a really nice number, 18. All right, you guys, I hope that helped. I hope that makes sense. These can be tricky. You have to just do a bunch of them. That's how you get good at math. I hate to tell you, but you're just going to have to do a bunch of them. Do the fun sheet, do the suggested problems. If you're not getting any of the answers I'm getting, you've got to contact me and we'll figure it out together.